Yashar Aval, as just he told. I work with Melissa and we work on underwater acoustic communication. Today I'm going to be talking about detection of OFDM signals over underwater acoustic channels. I will start with a short introduction to the underwater acoustic channel. Then I will talk about OFDM signals, and specifically I will focus on differentially coherent detection and a multi-FFT demodulation technique that we developed specifically for the underwater acoustic channel, and a few of other projects that our research team has been working on. And in the end, we will have a short demo which will show the multi-FFT demodulation technique working in real time, and hopefully live video transmission. So the issue with underwater communication is that electromagnetic waves do not travel far distances underwater. Therefore, if you are looking for any means of communication beyond a few meters, we are bound to using acoustic waves instead, because they can go much further. Acoustic waves, however, bring their own set of problems. For example, the bandwidth is very limited. It could be, say, more than 100 kilohertz if the distance is less than 1 kilometer, but then the usable bandwidth will shrink down to only a few kilohertz when we're looking at distance of 10 kilometers or more. This bandwidth, although very limited, is still, when compared to the carrier frequency, this signal is very wideband. What that means is that the properties of the channel at the lower frequencies could be quite different than what it is at the higher frequencies. This is in contrast to the wireless world where, for example, the 3G signal, although has 1.25 megahertz of bandwidth, when compared to the carrier frequency, it is very narrow band signal. So we expect all of the channel to follow the same statistics. Another property of acoustic channels is the long delay spread. As you see here, this is an ensemble of measured channel impulse responses from an ocean and an experiment conducted in the ocean. This figure shows that the delay spread for this specific channel, which is typically a rather short one, spans more than 3 milliseconds. That means if we want to be operating a single carrier mode, and say we're looking at symbol rates of 10 kilosymbols per second, we need an equalizer with 30 taps. Quite complex. Another thing that we see in this figure is that all these channel ensembles are measured during a duration of only 6 seconds. So this channel is very quickly varying, where in 6 seconds the channel has changed dramatically. If the channel is varying so quickly, it means we have severe Doppler shifts. This is a figure showing how this channel could vary both in amplitude and in phase. This is channel impulse response as it varies over time. So both amplitude and phase of the channel taps do change. That long delay spread that we just saw speaks strongly in favor of applying OFDM signals over this channel, because it would help us get rid of that long equalizer that was needed. However, OFDM signals in this channel have challenges other than the ones in the wireless world. In the wireless world, what we typically do is that we use one OFDM block to estimate the channel. Then that channel estimate is valid for the next few OFDM blocks. This is not true for the underwater channel. The channel is going to be vary so quickly that we need to estimate the channel for every OFDM block, or at least have some means of following the channel, tracking the channel from one OFDM block to the next in decision-directed mode. That's a complicated job to do. This is where perhaps another property of OFDM helps us out. which is, it makes differentially coherent detection feasible. If you wanted to do it in single carrier mode, having that long equalizer combined with differentially coherent detection is not going to work. Whereas with OFDM signals, we will see that it will work out pretty well. By the way, the plot here shows that shows the spectrum of the signal. When we transmit a 13 kilohertz tone, the received signal here shows an 8.7 hertz shift due to the motion, and you see some Doppler spread around that. So instead of receiving a tone at 13 kilohertz, we are receiving a tone with some spread due to motion. If we want to do differentially coherent detection with OFDM, we have two choices. One is to do it in time domain. If you want to do so, we are going to be comparing two adjacent OFDM blocks. And if you want good performance, we need more coherence between two adjacent blocks, which means we would be looking to have shorter OFDM blocks. The problem? The guard interval. Because of that guard interval, shorter OFDM blocks means lower rates. Therefore, we look into another form, which is in frequency domain. In this case, we compare two adjacent carriers. To increase the coherence between them, we need to pack more carriers into the OFDM block, making the OFDM block longer. The rate will go up. Therefore, we do differentially coherent detection in frequency domain to pack as many carriers as possible into the OFDM block. But then the question arises on how many carriers can be fit into the OFDM block? In this figure, the x-axis is the number of carriers. If you have too few carriers, differentially coherent detection is not feasible because that very assumption of differentially coherent detection is void, which is coherence between carriers. Carrier spacing is too high, not enough coherence between carriers. If we pack too many carriers, ICI, or inter-carrier interference, is going to limit the performance because this channel is varying over time and the orthogonality is going to be more. In this golden region in the middle, however, differentially coherent detection is feasible. In that range, we are interested to pack as many carriers as we can to increase the rate. What we aim to do, however, is to find means of compensating the Doppler so that we pack even more carriers into every OFDM block, increasing the rate, and we will see that it will be accompanied by improved performance at the same time. But one of the methods that we use for compensating Doppler is similar to what they do in wireless world, where they model the Doppler as a frequency offset. And they treat it just like a frequency offset and remove it. However, in our case, the problem is a little bit different because the Doppler shift at lower frequency carriers could be quite different than what the Doppler shift is at the higher frequency carriers. Therefore, a better method of fighting it is to resample it. To do so, what we do is we measure the length of the frame at the receiver using the preambles at the beginning and end of frame of OFDM blocks. Then we compare that to the original transmitted frame length and we resample the signal so that the length matches that of the transmitted frame. What we observed in experimental results is that this resampling removes the bulk of the Doppler shift, but we will still have some residual Doppler, which will cause inter-carrier interference. But before I go on to how we deal with the residual Doppler, let me talk about differentially coherent detection. When we do that in frequency domain, what we use is the assumption that the channel does not vary between two adjacent carriers. If that assumption holds true, differential equality detection follows on simply as division of the output of the FFT at two adjacent carriers. While that division works, perhaps a more interesting representation is multiplying by the conjugate of the neighbor. Because now we have that factor of the channel coefficient amplitude sitting beside our symbol. This is very helpful when we want to think of an array of receivers. In this case, all we need to do is sum those variables up, and the result very much resembles maximum ratio combined. This could also be represented in vector form, where differential equivalent detection can be followed as easy as that. But let us go back to the issue of the Doppler now. To deal with the residual Doppler, the most common approach that exists in the literature is equalization. Though I should remind you, this equalization is quite different than the one that we taught in the introduction. That was an equalizer with 30 taps, it was in time domain, it was very complex. This one, in most cases, you can get away with only 3 taps, and it operates over carriers. So basically what it aims to do is to remove the ICI due to that residual Doppler that we could not resolve with resampling. The issue with it is the performance. When the Doppler shift is large, that equalizer is not sufficient. What we do is based on a different vision on Doppler shift. One way to look at Doppler shift is that whatever frequency we transmit, receive the signal at a different frequency. Here's the Doppler shift. But another way of looking at it is that this channel is varying over time, so that the channel that we see at the beginning of the OFDM block is quite different than what channel we see at the end of the OFDM block. If we look at Doppler like that, one idea is that if the channel is time varying over the OFDM block, voiding the orthogonality requirement of OFDM, is that we cut the OFDM block into 2 segments. Then if we give each of these segments to a different FFT, and combine the 2 outputs of the FFTs with the correct weights, we can compensate for the channel variation from segment 1 to segment 2, therefore reducing ICI. A valid question is, how are we going to learn these weights? The method that we use and works reasonably successfully is to learn those weights in carrier by carrier mode using a very low complexity LMS algorithm. The algorithm starts with this few pilots and then goes on in direct decision-directed mode. To put this into a test, we use the results from an experiment. In this experiment, which is conducted in the ocean, we have the transmitter being towed with the ship, and we have an array of 12 receiver elements anchored to the seabed. The way the experiment works is that the ship starts towing the transmitter away from the receiver. The motion causes a great deal of Doppler. Then the ship turns around and moves towards the receiver. Every 4 minutes, the ship transmits 1 frame of OFDM blocks, represented here by 1 dot. So each dot is 1 frame of OFDM blocks being transmitted. And before I go to the results, this is one of the interesting figures that I thought I'd like to show you. This is a simulation based on the channel parameters measured during that experiment. Specifically, it's the sound speed profile. In this case, the sound speed profile is such that In the mid-water column, we have the minimum propagation speed. The effect of that is, as you see in the figure of acoustic intensity over a distance of 2 kilometers, that sound speed profile bends the waves towards the middle. In some means similar to what happens in the optical fiber, where the waves bend towards the slower propagating region of the medium. So let me show you the average mean square error performance. On the x-axis we have the log of number of carriers. As discussed before, if we have too few carriers, 128 carriers for example, 64 carriers, there's not enough coherence between carriers to follow on with differentially coherent detection, the differentially coherent detection phase. The black curve here shows the ordinary differential detection. As we pack more carriers into the OFDM block, we are reducing the carrier spacing. We're being more vulnerable to Doppler. Anywhere beyond 256 carriers in this case, ICI will limit the performance and detection will fail. This is where our multi-FFT algorithm, in this case we call it PFFT, kicks in. If we cut the OFDM block into 2 segments, we can improve the performance by about 3 dB. We can cut it down into 4 segments, the red curve, improve the performance even further. Even we can use 8 segments. With this method, what we can achieve is that we can increase the number of carriers 4-fold and improve the performance by about 3 dB. We also have other methods of doing the multi-FFT demodulation. As you see, a bunch of curves. All methods pretty much perform similarly. They by far outperform ordinary differentially coherent detection. And that can also be compared to coherent detection. This specific coherent detection algorithm is one that works by tracking the channel. It works in decision-directed mode, and if we have anywhere more than 256 carriers, it cannot track the channel from one OFDM block to the next. So it eventually loses track of the channel and it will fail. Even equalization cannot save it. So, in conclusion, we suggest application of differentially coherent detection to achieve better rates by removing the pilots, increasing the bandwidth by applying OFDM, and we see that we can actually outperform coherent detection in this specific channel due to the challenges of channel estimation. So, differentially coherent detection together with multi-FFT demodulation, we can achieve better rates and better performance at the same time. A few other projects that our team is currently working on is sparse channel estimation on underwater acoustic channels. Another one is live video transmission that we will have a demo on today. Statistical modeling of the channel. No widely accepted statistical channel models exist for underwater channels. Underwater acoustic and underwater sensor networks, and rateless coding. So let me move on to the demo. In this demo we have a transmitter, the amplifier, external sound card, and a very simple speaker. At the receiver side we have the external sound card again, the microphone, and this laptop will operate as the receiver. And the reason that we use external sound cards is solely because of their better signal to noise ratio performance and the extended bandwidth. The ordinary sound card on the computer cannot go beyond audible range, but these sound cards do. So we can extend the bandwidth beyond just 20 kilohertz audible range. The first code that I'm going to run, now let me run the receiver on this side. Where is the mouse? So what we have here is, let me pull this closer. So that's what you have. There is a setting issue with the device that I will solve. This is the amplitude of the channel impulse response. Is the amplitude of the channel response in frequency domain. Due to an issue that I think I can solve, beyond 20 kilohertz is being caught. We will fix that. This is showing the average BR over frequency domain. So when you see nulls, you just have elevated air and those carriers. This is the channel impulse response. And on this side, this one shows those combiner rates that we talked about. And specifically, I will move the transmitter, and you'll see how it affects combiner rate. In this figure, the red and blue, just a second, I'm not using the external sound card here. We are not using this. There we go. We are working with the laptop microphone. That's why all the bandwidth was being cut. Let me start MATLAB real quick. On that device this time. So now I will move the transmitter, introduce a little bit of Doppler into the channel. The red curve is the MSE value for our method. The blue one is ordinary differential coherent detection. And in this figure, we're showing the Doppler shift. So the combiner rates change. We detect the Doppler, and as you see, we compensated the effect of Doppler there, and the other way around. Getting closer, again you see the difference grows, and a similar effect you see here. The blue is the ordinary detection, the BR raises, while with the red, it is compensated. Another thing that I wanted to show was a very simple code. That, do we have any time left?
If you want to have no questions, you should stop. Sorry, 4:27 already. So.
Any questions?
You may have said this, but I
Good question.
That was what I was too.
It is a means of using more than one carrier in parallel. But specifically in OFDM case, you set the carrier spacing so that
What do the letters stand for?
orthogonal frequency